Hello everyone, my name is Finding Pepper and welcome to episode 3 of my Scratch 3D tutorial. In this video, we'll combine the wireframe render we made in episode 1 with the trifill we made in episode 2 to create something that can render solid 3D objects. Let's start by backpacking our trifill code. Then, go to your wireframe render and save it as a copy. Now, drag out the trifill from the backpack. We'll want to be able to draw triangles of different colors, so let's add a color input to our trifill block. Like so. Now, at the top of the block, we can simply set pen color to and then drag in the color input. Alright, now in episode 1, we drew shapes by using the draw line block many times, and manually entering coordinates to each block. For this episode, I am instead going to hold each of our triangles in a list, so we can easily access them in multiple places. I'll actually create two lists. One is for the vertices, which I'll call Vertices, for all sprites. The other is for the triangles themselves, which I'll call Faces for all sprites. Each vertex will have 3 entries in the list, an X, Y, and Z. Each face will have 4 entries, one for each vertex and one for the color. The reason I'm doing it this way is because I think it makes it a little easier to handle cases where several triangles meet. However, I could definitely be convinced that storing the vertex coordinates directly in the faces list is more efficient. Anyway, let's get back to coding. Why don't we create an easy way to add points and triangles to our world? Create a block called Add Vertex with 3 inputs, X, Y, and Z. Every block we create in this video will be run without screen refresh. Each vertex has 3 items in the list which represent it, so in this block, we'll simply add X to vertices, add Y to vertices, and add Z to vertices. Next, we'll make a block called Add Face. This will have inputs for each vertex, which I'll call V1, V2, and V3. And those will each store the index in the vertices list of that vertex. Now add 3 more inputs for the red, green, and blue components of the triangle's color. Start by adding V1 to faces, except each vertex has 3 pieces of data in the vertex list. So instead add V1 times 3 to faces. This way, we don't need to multiply by 3 when retrieving vertices from the faces list. Keep in mind that the first vertex is numbered 0, not 1, just to make things a little simpler. Now, we'll do the same thing for V2, so add V2 times 3 to faces, and then add V3 times 3 to faces. Now for the color, we're going to have to do something a little bit more tricky. Each of the red, green, and blue components can range between 0 and 255. So the way that Scratch stores color in a number is we first take the red component and multiply it by 256 squared, or 65536. Then we add the green component times 256. And finally, we add the blue component. You can think of this also like a 3-digit number in base 256. Alright, now when we start the game, let's just add a few vertices and faces to our world just for testing purposes. We'll start by clearing the lists, so delete all of vertices and delete all of faces. Then I'm going to place in a whole bunch of add vertex and add face blocks. You of course don't need to add the same vertices and faces as I do, but I think these make for good testing. So I'll just add those all in here real quick, and then you can copy from that. Now you might imagine that if you have a lot of vertices, it could get difficult to tell which index each one is at. To help with this, let's edit the add vertex block. add a label with 3 underscores, and then a number input, which I'll call IDX. Now, this input doesn't do anything, but you could use it to remind you which index each vertex is at. So for example, I can put in 0 to 4, like so. Finally, create a variable called dataAmount per face for all sprites, which will represent how many pieces of data each face has in the faces list. Set it to 4 when the flag is clicked. Now, for actually displaying the triangles. Edit the drawCube block and change it to be called Display World. Remove everything inside except erase all. We're going to be looping through the faces list, so create a variable called I to hold the index at each iteration. Set I to 1 at the start of the loop. Then repeat for each face, so that's length of faces divided by dataAmount per face. Each time, change I by dataAmount per face to move on to the next face. For drawing lines, we had 2 sets of x, y, z variables, one for each endpoint of the line. For triangles, we need one more coordinate. So create variables for the sprite only, called x3, y3, and z3. Then, just like we did with the other 2 coordinates, make a block to set the third coordinate, called setPos32, with inputs x, y, z. Inside, just set x3, y3, z3 to the block's inputs, like so. It would be nice if we had an easy way to take a trio of vertex numbers and set our 9 coordinate variables to the vertex positions. Create a block for this called getVertexCoordinates with inputs v1, v2, and v3. These inputs are really for the vertex numbers multiplied by 3, which is what we'll be working with basically all the time because each vertex has 3 items in the list. Because the vertices start at 0, to get the x-coordinate, we'll need to add 1 to the vertex number. For the y, we'll add 2, and for the z, we'll add 3. So we can just say setPos1 to item v1 plus 1 of vertices. That's the x. Then item v1 plus 2 of vertices for the y. Item v1 plus 3 of vertices for the z. Now we'll do the same for pos2, replacing all the v1s with v2s, like so, and then we will again do the same thing for pos3, replacing all of the v1s or v2s with v3s. So it should look like this when you're done. Now let's head back to our display world block. Here we'll need to do the same transformations that we did for drawing lines. But first, we need to set our position variables to the triangle's vertices using our new getVertexCoordinates block. So getVertexCoordinates of item I of faces, that's the first vertex, item I plus 1 of faces, and item I plus 2 of faces. So those are the indices of our 3 triangle vertices. Now we can duplicate our transformation code from drawLine. Those are the 6 blocks that set our position. So duplicate those and put them into the repeat loop, like so. Now for our transformations based on the camera position, rather than using the x, y, and z inputs, we'll need to switch those out for our newly set x1, y1, and z1 variables, and the x2, y2, and z2 variables as well. But we now have a third vertex too, so we'll need to get a setPos3 to, and then we can just follow the same model as with setPos1 and setPos2, and setPos3 to x3 minus camera x, y3 minus camera y, and z3 minus camera z. Likewise, for rotation, we'll need to also update our third coordinate. So setPos3 to z3 times sine y plus x3 times cos y, then y3, then z3 times cos y minus x3 times sine y. Then for our other axis of rotation, set pos 3 to x3, y3 times cos x minus z3 times sine x, y3 times sine x plus z3 times cos x. So here we're just switching out the 2's for the 3's, basically. So this code transforms the point in 3D space based on the camera's position and rotation. But now we need to actually project the point onto the screen. We'll do this in the same way we did in episode 1. And we'll use our pos1, pos2, and pos3 variables to hold the projected coordinates. So first, set pos1 to focal length times x1 over z1. And then y is focal length times y1 over z1. And then because we're projecting this into 2 dimensions, we can just leave the z coordinate blank. Now we'll do the same for pos2. Set pos2 to focal length times x2 over z2, and focal length times y2 over z2, and set pos3 to focal length times x3 over z3, and focal length times y3 over z3. And finally, we'll just plop in our trifill block. As the inputs, we'll put in the coordinates of our vertices. So x1, y1, x2, y2, x3, and y3. For the 7th input, that is resolution. And I could just put in some arbitrary number like 2, but why don't we make a variable for that so we can change it easily? I'll call that tri-res, short for triangle resolution. Alright, I'll put that tri-res variable in the 7th input. And at the start of the game, we'll set tri-res to 2. Then we have one more input in our trifill block, and that is for the color. Remember, we stored the color in the 4th item for each face. So we'll put in item I plus 3 of faces for the color input. Okie dokie. This should be all we need to get some triangles displaying on the screen. Let's run it, and indeed, you should see some triangles. However, they're not layered properly. I'll cover layering more towards the end of the video, but for now let's implement something called backface culling, which will help a little with this layering issue as well as improve performance. With backface culling, only triangles that face towards the camera will be drawn. That way, the backsides of polyhedra like our pyramid here will be invisible. Which side is considered to be forward depends on the triangle's vertex winding. So if the vertices go in a clockwise direction in relation to the camera, the triangle will be drawn. But if they go in a counterclockwise direction, i.e. you're looking from the backside, it won't. Before we implement backface culling, we need to learn a little about vectors and their products. A vector can be thought of as an arrow, and simply records a position or change in position. In 3 dimensions, which is what we'll be working with, a vector has 3 components, an x, y, and z. We also sometimes refer to a vector's magnitude, which is just its length. Now vectors can be multiplied together in 2 different ways, the dot product and the cross product. Both of these products are very useful when coding a 3D engine, so let's discuss what each one does. The dot product measures the similarity between 2 vectors, and outputs a single number. There are 2 ways to write the dot product. One, the geometric definition, is the product of their magnitudes and the cosine of the angle between them. The other equivalent definition is to individually multiply their x, y, and z components, and then add them together. In 2 dimensions, it's the same, just without the z component. Now to understand a little better what the dot product is doing, let's rotate the vectors such that one is pointing along the x-axis. We can do this because, looking at the geometric definition, the dot product does not depend on their orientation in space, only the angle between them. Once we do this, the y component of the first vector becomes 0, and thus the y drops out of the equation entirely, leaving just the product of their x components. So this means the dot product is essentially a measure of how much the second vector points in the same direction as the first vector, or vice versa. If the dot product is positive, the vectors point in similar directions. If it's negative, they point in opposite directions, and if it's 0, they are perpendicular. That is, at a right angle to each other. Now the cross product is a little trickier to calculate, but the concept is simple. The cross product of two vectors results not in a number, but in another vector, which is perpendicular to both of the two multiplied vectors. This new vector is called the normal vector. You might notice that the normal vector points upwards if the first vector is to the right of the second, but downwards if the first vector is to the left of the second. Thinking back to backface culling, you might see how the cross product could be useful. Both backface culling and the cross product depend on what order the vertices are in, whether it's clockwise or counterclockwise. So we can say that if the normal points towards the camera, the triangle is front-facing, and if it points away, it's back-facing. Then the dot product can be used to determine whether the normal is pointing in the same direction as a vector from the triangle to the camera. Okay, hopefully that made some sense to you, but if not, feel free to ask about it in the comments, and I'd be happy to answer your questions. Let's go ahead and put that into Scratch. First, I'll make blocks that can calculate the dot product and the cross product. Let's start with the dot product because it's simpler. Make a block called dot. This will have 6 inputs, the first 3 for the first vector, x1, y1, z1, and then the second 3 for the second vector, x2, y2, z2. Let's make a new variable called dot for the sprite only to hold the result of this block. Inside the block, set dot to x1 times x2 plus y1 times y2 plus z1 times z2, just like we talked about. Okay, that wasn't so hard. Now for the normal vector. Make a block called getNormal2Triangle. This one will have 9 inputs, 3 each for the 3 points of the triangle. The first 3 we can call AX, AY, AZ, then BX, BY, BZ, and finally CX, CY, CZ. Again, we'll create a variable to hold the result of this block, except in this case we need 3 variables because the result is a vector with 3 components. So let's make a variable normal x for the sprite only, normal y, and normal z. And all of those will be for the sprite only. Now, the math that goes into calculating the normal vector is kind of tedious. And honestly, for this, you don't really need to worry about why these specific quantities are multiplied. It follows pretty directly from the definition of the cross product, just with a whole bunch of annoying math. So let's set normal x, get a minus and a times, cy minus by, times az minus bz. That whole thing minus cz minus bz times ay minus by. Now, one thing of note here is that when we're subtracting one value from another along the same axis, like cy minus by, those represent a difference in coordinates and thus represent one component of a vector from the second coordinate to the first coordinate. For example, cy minus by represents the y component of the vector from b to c. Alright, let's keep going. Normal y and normal z follow a similar pattern, so let's set normal y to cz minus bz times ax minus bx. That whole thing minus cx minus bx times az minus bz. Set normal z to cx minus bx times ay minus by. That whole thing minus cy minus by times ax minus bx. Phew. Okay, that's how to calculate the normal vector. It's not pretty, but it works, and that's what matters. Let's go ahead and use these blocks to implement backface culling. Inside the loop in display world, right after we get vertex coordinates, let's first get the normal vector to our triangle, x1, y1, z1, x2, y2, z2, x3, y3, z3. Like we said before, the normal vector will be used to tell whether the vertices are wound clockwise or counterclockwise in relation to the camera position. So we want to tell whether it's pointing towards the camera or away from the camera. So now let's compute the dot product of the normal vector and a vector pointing from any point on the triangle to the camera. Let's just choose pos 1 as that point on the triangle, and we can find that vector with camera x minus x1, camera y minus y1, and camera z minus z1. Now for the remaining three inputs, we'll put in our normal x, normal y, and normal z. Now we only want to draw the triangle if these are pointing in the same direction. That is, the dot product is positive. So around the rest of the code inside our loop, let's check if dot is greater than 0, and only run the code if so. Make sure though to move the change I by data amount per face outside of that if check, so we still move on to the next face. Otherwise we'll just keep trying to draw that same face over and over again, and that would be no good. Okay, let's try running that. And there you see the back faces of our little pyramid there are no longer visible. Yippee! Now there are still some layering issues, of course, but before I fix that, let's talk about clipping. We talked about clipping lines in episode 1, and clipping triangles certainly is more difficult than clipping lines, but it's actually not too bad. And because triangles are essentially made of lines, we'll still make heavy use of our line clipping code from episode 1. With this in mind, let's create a block to clip a line called clipLine. Add inputs for the two endpoints of the line, which I'll call x1, y1, z1, x2, y2, z2. We'll want this code to work for any pair of vertices, so rather than modifying the actual vertex position variables, let's create 3 new variables for this sprite only, called clipx, clipy, and clipz, which will hold the position that our line was clipped at. So the clipLine block will specifically clip the end of the line that the first vertex is on, and we'll set the clipx, clipy, and clipz variables to where the line should be clipped to. Oof, I said clip a lot there, and don't worry, I'm going to say it a lot more. Let's bring our clipping code into this block. To review, we first find the percent of the line we want to clip by setting clip percent to near clipping plane minus z1 over the length of the whole line, which is z2 minus z1. Then we find the actual position that's that percent along the line. So we set clip x to x1 minus the length of the line, x1 minus x2, multiplied by clip percent, and set clip y to y1 minus the amount of y that we need to clip off. And finally, clip z will just be the near clipping plane. Now I'm going to have the triangle clipping code also be responsible for actually drawing the triangle, because in some cases we need to draw multiple triangles when clipping. When clipping a triangle, either one point is behind the near clipping plane, or 2 points are behind the near clipping plane. If all 3 are, then we just don't need to draw the triangle at all. I'll make a custom block to handle each of those 2 cases, starting with the case where 2 points need to be clipped. Call this block drawClippedTriangle dash 2 points, and I abbreviated points. Then we're going to have a whole bunch of inputs for the 3 points of the triangle as well as the color, because we will need to draw this. So those will be x1, y1, z1, x2, y2, z2, x3, y3, z3, and color. This block will assume that points 1 and 2 are behind the plane, while point 3 is in front of the plane. So we need to clip off points 1 and 2. So we'll start with point 1, use our clipLine block with inputs x1, y1, z1, x3, y3, z3. So clipping off the line from point 3 to point 1. Then we'll move our point 1 to that clipped position, set pos 1 to clip X, clip Y, clip Z. Now we need to do the same for point 2. Clip line X2, Y2, Z2, X3, Y3, Z3, and then set pos 2 this time to the clipped position. Okay, so we've clipped our line in 3D space, and as before, we need to actually project that point onto our 2D screen. We can use basically the same projection code that we used in Display World. So let's go up there and take out the projection code plus the try-fill block. That is the last 4 blocks of our loop here. And we'll just drag them all the way down to our clipping code. We can leave these mostly unchanged, except for our pos 3. There we'll need to replace the pos 3 variables with the pos 3 block inputs. Because, unlike pos 1 and pos 2, we haven't clipped pos 3, we've just left it unchanged. And then in our try-fill block, make sure to continue to use the try-res as the 7th input, and as the 8th input, that is the color, we will use the color input from our clipping block, like so. So that code will work to draw a triangle with 2 points clipped. Now for the case where we only clip off 1 point. Make a block called draw clipped triangle dash 1 point, colon, with a bunch of inputs, x1, y1, z1, x2, y2, z2, x3, y3, z3, and color. And I forgot to create the color input in my recording, but you should just do that yourself. The case where just 1 point is behind the plane is actually a bit harder. In this case, when we clip off that point, our triangle turns into a quadrilateral. Now this isn't too big of a problem, because to draw a quadrilateral, we can just draw 2 smaller triangles. However, we do have 4 points to consider instead of 3, and you can probably guess where this is going. We should probably make a 4th set of position variables to hold that 4th point. So make with me variables for this sprite only, x4, y4, and z4. Like with our other 3 sets of position variables, we'll create a custom block to set these variables. I'll call it set pos4 to x, y, z, and then we'll do the same thing inside it as we did with the other 3, set x4 to x, set y4 to y, and set z4 to z. We can now go back to our draw clipped triangle block and start clipping those lines. Now I'm going to assume that point 1 is the point that we need to clip off. But there are 2 lines connecting to point 1. There's the line from point 1 to point 2, and the line from point 1 to point 3. We'll need to clip both of them and get clip positions for both. That's why we have 4 variables now instead of 3. We'll start with the line between x1 and x2. Clip line from x1, y1, z1 to x2, y2, z2. We'll hold this position in our pos1 variables. So set pos1 to clip x, clip y, clip z. Now we need to clip the line from point 1 to 3. So use our clip line block again from x1, y1, z1 to x3, y3, z3. And for this one, we'll use our pos4 variable to hold the clipped position. So set pos4 to clip x, clip y, clip z. Alrighty, now we've got our 4 points of the quadrilateral. We'll need to project all 4 of those points onto the screen. And we'll do that in exactly the same way as we did before. But for pos 2 and 3, those have not been clipped, so we can just use the inputs to the block for those. Now for pos 4. It should not come as a surprise to you that we'll be using our pos 4 variables for these. Okay, now that we're done with that, let us use our try-fill blocks. Now we'll need 2 of them, because it's a quadrilateral, so it's made up of 2 separate triangles. The first one will be try-fill from x1, y1, x2, y2, and x3, y3. Now for our other triangle, and make sure to put the points in the same order as I do here, so as to preserve the vertex winding. We'll try-fill from x3, y3, x4, y4, to x1, y1. Again with try-res and color. So those 2 together will draw our projected quadrilateral. Now, these two blocks are all well and good, but we need some logic as to when to use each one. So let's make a big block to handle all the different cases where each particular vertex is either behind the clipping plane or in front of the clipping plane. I'll call that block draw clipped triangle with v1, and then 3 inputs, x1, y1, z1, v2, colon, and then 3 more inputs, x2, y2, z2, and then v3, colon, x3, y3, z3. And of course we'll need a color input, so say color colon, and then a color input. Just like that. Okay, now each of our vertices could either be behind the clipping plane or in front of the clipping plane. We know one of the vertices is behind the clipping plane if its z component is less than the near clipping plane, because we've already transformed it so it's where it should be in relation to the camera. Now there's 2 cases for each vertex. It's either behind the plane or in front of the plane, and there's 3 vertices, so that's 2 to the 3 cases, or 8 different cases. So let's get ourselves an if-else and start checking. First we'll check if z1 is less than the near clipping plane. Then inside that, get another if-else, and check if z2 is less than the near clipping plane. Alright, inside that you might think we would also want to check if z3 is less than the near clipping plane. However, if all 3 of the vertices are behind the near clipping plane, then we don't need to draw the triangle at all. That's one of our 8 cases that we just don't have to worry about. So we'll just check if not z3 is less than near clipping plane. If so, well, we need to clip 2 points off, that's point 1 and 2. So we'll use our corresponding block. Draw a clipped triangle with 2 points. Remember, the first 2 sets of coordinates that we input to this block are the points we want to clip. So as inputs we'll give x1, y1, z1, x2, y2, z2, and then x3, y3, z3, and finally the color input. Alright, 2 of our 8 cases down. Now let's examine the else condition. That means our point 1 should be clipped, but point 2 should not be. Now here there's 2 cases again. Should we clip off the 3rd point or not? So we'll check if z3 is less than near clipping plane. Now if so, that means 2 points need to be clipped off. Those are points 1 and points 3. So we'll use our draw clip triangle with 2 points block, with pos 1 and pos 3 as our first 2 inputs. Now to preserve the vertex winding, we need to make sure that the coordinates stay in the same order. So we need to put position 3 first and then position 1 second. So as inputs, x3, y3, z3, x1, y1, z1, and x2, y2, z2 is the point that we don't want to clip. Alright, 3 out of 8 cases down. Now in the else of that if-else, we have only z1 behind the near clipping plane. So we only need to clip that 1 point off. We'll use our draw clipped triangle with 1 point for this case. Point 1 is the one we need to clip off, so it's going to be the first input. So we have as inputs x1, y1, z1, x2, y2, z2, x3, y3, z3, color. Alrighty, we're halfway there. Now we need to examine all the cases where point 1 is in front of the near clipping plane and shouldn't be clipped off. Again, we'll check with an if-else if z2 is less than near clipping plane. And then inside that, we'll check with an if-else if z3 is less than near clipping plane. Inside our first case, we have z2 and z3 behind the near clipping plane, whereas z1 is in front, so we need to clip off points 2 and 3. We'll use our draw clipped triangle with 2 points clipped block, remembering to put points 2 and 3 first because those are the ones we want to clip off. Passes inputs x2, y2, z2, x3, y3, z3, x1, y1, z1, and color. Alright, 5 out of 8 done. Are you getting tired yet? I know I am, but we've got to keep going. In the else of that if-else, that is where z2 is the only point behind the near clipping plane. So use our draw clipped triangle with 1 point block, pass in as the first inputs x2, y2, z2. Now vertex 3 always has to follow vertex 2 to preserve the vertex winding, so we'll then put x3, y3, z3 as our next inputs, and then finally x1, y1, z1, and then color. Now in our final else case, let's get one more if-else, again checking if z3 is less than near clipping plane. In this case, Z3 is the only one behind the near clipping plane, so we need to clip it off. We'll use our draw clipped triangle with 1 point block, making sure to put x3, y3, z3 as the first inputs, then x1, y1, z1, then x2, y2, z2. We've just got one more case down, and this is the case where none of the points need to be clipped. Well, we've already done that. We can actually just go to our display world block and grab those final 4 blocks of our code, the 4 blocks that project the coordinates and draw the triangle, and put them in the else case. Okie dokie. That was a bit tiring, but at least now we have some clipping code that hopefully works. Now it's very easy to have misplaced a variable or two in that process, so perhaps it won't work first try, but if it doesn't, my guess is that you just need to go through and make sure everything looks to make sense. We need to use this draw clipped triangle in our display world block. That will be right at the end of our drawing loop, where we'll draw a clipped triangle with v1 as x1, y1, z1, v2 as x2, y2, z2, and v3 as x3, y3, z3. And our color will remain item I plus 3 of faces. Let's run the project and see what happens. If we move our camera inside of our pyramid, we should not see any weirdness. We should just go right inside and have the pyramid nicely disappear. If we put the camera kind of on the edge of the solid, you should be able to see that triangle getting clipped before your very eyes. Again, this is an easy place to have misplaced a few variables, so if something doesn't look quite right, you might want to go and check over things. But for me, this is looking great. With clipping done, that just leaves depth sorting to take care of. I'm going to use something called Painter's algorithm, a simple yet fast method that draws triangles farther away first so that closer triangles will draw on top. Now this algorithm isn't perfect. Sometimes the triangles will not get layered exactly correctly, especially if they're very large or kind of long and skinny. And it's certainly the only thing that is practical to use in Scratch, because Scratch has such bad performance. So Painter's algorithm just sorts the triangle based on the distance to the centroid of the triangle. And the centroid is the average of the positions of the 3 vertices. So we don't have to find the centroid every frame when we want to sort the faces. Let's calculate the centroid's position at the start of the project and store its position in the faces list. That's going to be 3 extra pieces of data for each face, so when the flag is clicked, set data amount per face to 7 instead of 4. Inside the add face block, we need to calculate the average of the positions of the 3 vertices. This is a little annoying to do, which is why we're doing this right at the start so we don't have to do it all the time. We'll start with the average x position, so add to the faces list, and then we'll need to add together the 3 x positions of the vertices, and then divide that by 3. So that is item v1 times 3 plus 1 of vertices. The v1 times 3 is to find the first vertex, and then the plus 1 is to find the x-coordinate specifically. Now we add item v2 times 3 plus 1 of vertices, and then we add to that item v3 times 3 plus 1 of vertices. Now that's the sum of the 3 x positions, and we now need to divide by 3 to get the average. So go ahead and do that. Divide that all by 3, and add the results to the faces list. Now, for the average y-coordinate, we're going to do exactly the same thing, except instead of adding 1 each time, we're going to add 2 to find the y-coordinate in the vertices list. Likewise, for the z-coordinate, we'll replace all those plus 2's with plus 3's. Okie dokie. Now for actually sorting the faces. I'm going to go with a method called merge sort. Now, just as a disclaimer, I've coded this implementation myself, so if you lovely viewers spot any issues or inefficiencies, don't hesitate to let me know in the comments. Now, merge sort works by splitting a list into little sublists of size 1 each. From this, we want to create sorted sublists of double the size. To do this, we go through each pair of sublists and look at the first item of each. Whichever first item is smaller, we move to the front. Now we do this with every pair of sublists. Now we have a bunch of sorted sublists of size 2 each, and we want to combine each pair of those into a sorted sublist of size 4. So we do the same thing we did before with all of our larger sublists, repeatedly comparing the first item in each of the sublists and adding the smaller one to the front of our new, longer sublist. We repeat this until the entire list is sorted. Now let's look a little more closely at how to combine the two sorted sublists into one sorted list. Let's define two indexing variables, I and j. I will be the start of the first sublist, and j will be the start of the second. We compare items I and j of our list, that is, the first items of each sublist. Now we want to sort the list such that the items earlier in the list are smaller. If instead the item at j is smaller, we remove it and insert it at I, and then increase both indexing variables. We increase I because our sorted list is being built up to the left of I, and we increase j to move on to the next item in the second sublist. If instead the item at I is smaller, we can leave it where it is and just increase I, indicating that it's now part of the sorted list. We continue this process until we've repeated through the whole list. You may wonder, though, how this will work when we have multiple items in the list associated with each face. We need to move them all at once and make sure they stay properly ordered. This is actually quite simple to do, especially because we always want to move an item to an earlier position and never a later position. To do this, we just repeatedly take the last piece of data from the item we want to move and move it to the index where we want it to be. And it's as simple as that. We can now begin coding this in Scratch. Create a block called depth sort faces. We'll need some new variables to help with our algorithm. The first will be group size. All of these variables will be for this sprite only. This variable will hold the size of the sorted sublists at each stage. Let's make another variable called list length, and that'll just hold the amount of faces in our list. We already have a variable called I, but remember we needed two indexing variables for this, so make another one called j. Now we'll create variables to hold the current depths that we're comparing. I'll call those variables depth 1 and depth 2. And we'll make one more variable called current size, and this we'll use in cases where our list length is not an exact power of 2. Okay, we've got our variables, let's begin coding. We'll start by just setting the group size to 1. Now we'll set list length, and remember, this is how many faces we have. So that is equivalent to the length of faces divided by how many pieces of data there are per face. Alright, now we'll have a big loop that will repeat for each of the different sizes of sorted sublists, starting with size 2, and then going to size 4, then 8, then 16, then 32, etc., doubling each time. Now you can see that if our list length is 2 to the 5th long, say, that we'll need to repeat 5 times, because we'll need the group size to double 5 times. And if it's 2 to the 6th long, we'll need to repeat 6 times. What we're describing here is that we need to find the log base 2 of our list length. Scratch can't take log base 2, but it can take log base 10. And we can get the logarithm of any base in terms of a different logarithm. So we're going to use a repeat loop first of all, because we'll need to be repeating. And then we'll take the ceiling of, then we need to do our log base 2 of list length, and that is equivalent to log of list length divided by log of 2. Log rules are something that you might learn in pre-calculus. If you haven't gotten there, don't worry, you can just take my word on it for now, and maybe do some independent research if you're curious. Alright, well, each time we loop, we'll need to double the group size. So set group size to group size times 2. The idea is that by the end of the loop, our group size will be greater than or equal to the length of our faces list. Alright, now let's start with our I variable. This is the first of our two indexing variables, and it will hold the index at which our first sorted sublist starts. Of course, we'll want to start at the very first sorted sublist, so set I to 1. Now, we need to go through each pair of sublists. So repeat list length divided by group size. That is how many pairs of sublists we have. Our j variable now is going to hold the index of the start of our second sorted sublist in the pair. Since each sorted sublist in the pair has size group size over 2, we'll simply set j to I plus group size over 2, and then because each of our faces has multiple items in the faces list, we'll multiply that by data amount per face to get the actual index in the list. Now we need to read the depths of the two faces in our pair that we're comparing. We'll start with the face at position I. That is the first face in the first sorted sublist. Let's just use our pos1 variable to hold that depth. So let's set pos1 to, now we need to get the difference between the centroid of the triangle and our camera position. So set pos1 to item I plus 4 of faces minus camera x, then item I plus 5 of faces, the y position of the centroid, minus camera y, and then item I plus 6 of faces minus camera z. Okay, now the pos1 variables hold the difference between the camera position and the triangle's position. We don't just want the difference though, we want the actual distance between those 2 points. To find that distance, we can use the distance formula. That is, the distance equals the square root of the x difference squared plus the y difference squared plus the z difference squared. Now you'll notice that that formula does have a square root in it, which isn't ideal because square roots take quite a while to calculate for computers. Luckily for us, we can actually just remove that square root from our formula, because we don't actually care about the actual value, we just care if it's greater than or less than other distances. So if we just use the squared distance for everything, we'll get exactly the same results. Okay, let's set our depth1 variable to this first squared distance between our camera and the first triangle. That is x1 times x1, or x1 squared rather, plus y1 times y1, plus z1 times z1. We've now gotten the distance between our camera and the first of the 2 triangles we're comparing. To get the distance between our camera and the second of those 2 triangles, we'll do exactly the same thing, except we'll use our j variable instead of our I variable, because our j variable holds the index of the second triangle that we're comparing. So set pos2 to item j plus 4 of faces minus camera x, item j plus 5 of faces minus camera y, and item j plus 6 of faces minus camera z. We'll set depth 2 in the same way we did depth 1. That is, to x2 times x2 plus y2 times y2 plus z2 times z2. Make sure you're using the pos2 variables for this one. Now we need to go through our 2 sorted sublists and comparing the first item of each and moving the lesser one to the newly sorted sublist of double the size. Before we do all that though, let's just address the possibility that our sorted sublists might not be the full length long. Let's check with an if-else. First, get I divided by data amount per face. This will get what number face it is, basically. Now we'll add to that group size. And remember, group size is how many faces we're expected to have in the pair of 2 faces. So when we add group size to I divided by data amount per face, we'll get the expected number of the final face in the 2 sublists we're comparing. And we'll check if that is greater than list length. if it is greater than list length, what that means is that the size of the two lists that we're currently comparing is not as big as the group size, that is kind of the expected size. But when that is the case, we just need to make sure we account for that. And that's what our current size variable is for. If we do have fewer faces than expected, we'll set current size to the total list length minus, and then the floor of I divided by data amount per face. So it's basically just getting how many faces are there between I and the end of the list. Otherwise, that means there is at least as many faces as make up a full group between I, our starting index, and the end of the list, so we can just set current size to group size. So we found our current size. That is the exact amount of faces among both of our two sorted sublists. And remember, we're going to be merging those two sorted sublists, so let's get a repeat loop. And we're going to need to repeat through all of those items, so we'll repeat current size, and then subtract 1 for that because the last face is guaranteed to be in the right spot after we've sorted all the others. Okay, inside that loop, first let's make sure that j, the starting index of the second sorted sublist, is greater than I, the starting index of the first sorted sublist. If this isn't the case, that just means our first sublist is empty, and we don't need to continue with the loop if that's the case. Now we're sorting our list so that the greatest depths are actually at the front of the list, because we want to draw the triangles with the greatest depth first so that we can draw triangles that are closer to the camera on top of them. That means that ideally, depth 1 would be greater than depth 2. But it's possible that the first depth in the second sublist is greater than the first depth in the first sublist. That is, if depth 2 is greater than depth 1. So let's get an if-else statement and check that. And to this condition, we should also make sure that our second sublist still has some items in it, that is, j is less than length of faces. Okay, now in this case, if depth 2 is greater than depth 1, then we need to move that face at index j back in the list so that it comes before depth 1. In other words, we need to move the face at index j to be instead at index I of the list. Remember how we talked about doing this. We just repeatedly take the last piece of data from our second face and insert it to the index where we want it to be. We want to do this for all pieces of data for our face. So repeat data amount per face, then insert item j plus data amount per face minus 1 of faces at index I of faces. And now we're moving it, so we need to make sure to delete the item where it was before. So delete item j plus data amount per face of faces. Now this is a small little thing, but we're calculating j plus data amount per face multiple times in the same loop. And we could instead just calculate it once before we loop through each of the pieces of data. So let's do that. Make a variable called j plus d for this sprite only. Then, before our little loop here, set j plus d to j plus data amount per face. Then in the two places we use j plus data amount per face, replace those with our new j plus d variable. It's worth noting that in the second occurrence of this, we don't subtract 1 because we inserted a new item in the list before it, thus increasing the index by 1. So we've removed a face from our second sorted sublist. That means we need to move on to the next face in our second sorted sublist. Remember that j is the index of the first face in our second sorted sublist, so we need to move j on to be at the next face. So change j by data amount per face. Now this is a new face. That means we need to recalculate what depth 2 is. To do that, we can simply duplicate our code to find it from above. That is the set pos 2 and set depth 2 blocks. Just like so. Now we always need to increase our I variable, because either, as in this case, we've just moved a face into the spot where the I variable was, and so we need to increase it, or we've decided that the first face in our first sorted sublist was in the right spot, and so we can increment I to move on to the next face in the first sorted sublist. In both cases, you can think of it as building a new, larger sorted sublist in the indices leading up to I, Now when we move the face at index j to index I, and then increase I, the face at I will be the same face that was at I before, it'll just be in a different position. So we don't need to recalculate depth 1 there. However, in the else case, when the face at I was in the right spot, well, then we need to move on to the next item in our first sorted sublist. So we need to reset our depth 1 variable in that case. So in the else condition, we can duplicate those blocks that we used above, setting pos 1 and setting depth 1. Okay, now at the end of the loop, we'll change I by data amount per face as we described. Remember, we always want to do that to move on to the next face. And then just outside of the loop, we're going to change I by data amount per face once more, and that will move us on to the next pair of sorted sublists. Now our repeat loop will do that over and over again for each pair of sorted sublists. It will take them and it will merge them together into one sorted sublist of double the size. And then our outermost repeat loop will repeat that for each of our sizes, all of the powers of 2, until we get to a size that is as big or bigger than the length of the list. And we'll be left with one final sorted sublist, which isn't really a sublist anymore, it's just the entire sorted list. Alrighty, and that is our depth sorting code done. I realized that I probably didn't explain it as well as I could have, so sorry about that if that is the case. I encourage you to ask about it in the comments if you have questions. We need to use our depth sort faces block in the main loop. And so just plop it right there, like so. And then we should be able to run the project and see that our green triangle in the back is indeed appearing behind our blue pyramid. Okay, that's really great. We've now covered everything that I wanted to get to have a functioning 3D renderer that will be able to render most scenes pretty seamlessly. And that brings us to the end of this episode. I hope you enjoyed this tutorial. Have a great rest of your day, and goodbye!